Hi, in this video we consider another problem with two acids. But unlike the last problem where the Ka's of the two acids were very different from each other, in this problem the Ka's of the two acids will be quite similar. So in this problem we have again 1 liter of water and 1 mole of HF. And now we have 1 mole of formic acid, HCO2H. And we want again to find out the amount of dissociation of both acids. But the difference now is that while the Ka of HF is unchanged, 6.3 times 10 to the minus 4, formic acid, HCO2H, is only slightly weaker. It's 1.8 times 10 to the minus 4. It's only half an order of magnitude smaller than that of HF. And that means that when we set up the ice problem, we're going to have to consider both reactions at the same time. And so let me write them down. That's the first reaction, but now we'll consider the second reaction. And again, we'll consider the E line, and we'll use X for the amount of HF that's associated, Y for the amount of formic acid that's associated. We again started off with the initial molarities of 1.0, so 1.0 minus X, and 1.0 minus Y. But now we have the H3O pluses coming from both reactions. The first reaction with HF produces some H3O plus, and the second reaction also produces some. So the H3O plus is now X plus Y. And so when we do that, we're going to end up with these as our two expressions. We take the concentration of the products equals the equilibrium constant. Over here we have Y times X plus Y. And now please pause the video and see what progress you can make on deducing orders of magnitude. Okay, so we see that in both cases the Ka's are quite small compared to the initial molarity. So we assume that both X and Y will be small compared to 1. And so we're going to get the order of magnitude of 1.0 minus X is 0. And the order of magnitude of 1.0 minus Y will also be 0. We know the Ka's, order of magnitude of the Ka of HCO2H is, we're going to take it as minus 3.5. And the order of magnitude of KaHF is negative 3. So the HF acid is stronger than the formic acid, and therefore we're going to assume that most of the H3O plus that's going to be produced is from the HF, and if with that assumption, we are going to believe that the order of magnitude of X plus Y, since most of it's coming from the HF, it's the stronger acid by half an order of magnitude, it will be the same as the order of magnitude of X. So that's the assumption that we're going to make. So pause the video and see with this initial information whether you can now solve for the orders of magnitude of everything. So we have that the order of magnitude of the denominator here is 0. The order of magnitude here is -3. And these two terms have the same orders of magnitude. Therefore, they each have orders of magnitude -1.5. The order of magnitude of x is -1.5. And the order of magnitude of x plus y is -1.5. We can now put that over here on the other expression. You have order of magnitude 0 in the denominator here, -3.5 here. X plus y is order of magnitude -1.5. And that makes y's order of magnitude -2, since -2 plus -1.5 is -3.5. Okay, so we're making a lot of progress. Now that we have the orders of magnitude, let's see what you can do to solve for the actual values of x and y. And we're going to need some algebra. Please pause the video and work on that, and then come back. So, great. So, the order of magnitude of x is -1.5, and the order of magnitude of y is -2, and that means by the 5% rule that these terms can be ignored. And now what we're going to do is we're going to take the equation, the remaining equations that we have, and we're going to write them in the following form. The top equation is x times x plus y, 6.3 times 10 to the -4, and we're going to divide by the second equation. Y times x plus y is equal to, dividing by 1.8 times 10 to the -4. And we see that these two terms here cancel. And we now get that the ratio of x to y are x equals, when you work that out, 3.5y. So please pause the video and calculate what the values of x and y are, and we'll compare answers. So when I do that, I find that x is 2.2 times 10 to the -2, and y is 6.3 times 10 to the -3. Let's check. 2.2 times 10 to the -2 is order of magnitude -1.5, and 6.3 times 10 to the -3 is order -2. It is exactly as predicted. And we can see that by half an order of magnitude more, the X, the stronger acid, by half an order of magnitude produces that much more of the H3O+. And we'll practice this more complicated problem again in tomorrow's lab.